normal coordinates is like that. X dot, sorry, Z dot equals U, and W dot is a certain X prime LW U, where LW is some skew-symmetric matrix depending smoothly on W. The curve gamma is just a vertical. Is 0 W. And just as in the three-dimensional case, you get easily, you set that key of W is just a norm of to norm of the matrix N, and again easily you find the estimate that that the metric complexity is larger than 1 over epsilon square okay, you get this estimate exactly as in the previous case. Then now what you would like to do, first it is clear that you see these are normal coordinates. If you make a change, if you make just a change of coordinate, which is a rotation of Z depending on W, that is if you put the tilde equal H of WZ, you do not change the fact that you do not change anything, because it preserves the fact that Z tilde is new normal coordinate again, and the curve gamma is still this guy. Then you can do this, and if you can do this, then it means that you can consider that this LW is block diagonal, in fact. It's 2 by 2 block diagonal. Skew-symmetric matrix, 2 by 2 block diagonal. Then the question becomes the following. You are given a one-parameter family, a smooth one-parameter family of skew-symmetric matrices. Can you smoothly diagonalize it? So it is well known that if it is not only smooth but analytic, you can. It is theorem of Cato.
Oh, really? I think it is an old one, right?
Older, but okay. You can find it. In the analytic case, you can. The question is whether, when in the smooth case, you can. In fact, generically, in generic situation for us, it is clear that you can, because for the following reason. As I already said, the codimension of the set of bad skew-symmetric matrices, that is skew-symmetric matrices that have a double eigenvalue, is 3. Codimension of B in the set of bad set of skew-symmetric matrices, those that have double eigenvalue is 3, and it is clear also that if the eigenvalues are simple, then you can find simple you can find smooth eigenvector, and you can find smooth eigenvector, and you can smoothly diagonalize. But here since here, okay, here we have one parameter family. Generically, it will not cross this bad set of codimension 3. Then generically we can smoothly diagonalize. But in fact there is more than that. What we prove with Akayukin, I don't know, we don't know if it was known before, but it is that not only generically, but so this is general theorem, but not only, this is true not only generically, but the bad set in fact has infinite codimension. Infinite codimension. I don't know if I have to give details about that, maybe. It is quite interesting result. It is result of not obvious at all. But anyway, let us forget about that. It is enough to see that in our case, in generic situation, we can smoothly diagonalize. Okay, so since we can smoothly diagonalize, this matrix is diagonal. I may assume that the first, and the norm that appeared here is just the modulus of the largest eigenvalue. Then what you have? Then what you have? You see that in fact this L, so L is in fact alpha 1 W minus alpha 1 W block alpha 2 W minus alpha 2 W, etc. And alpha 1 is the norm. Is the norm of L, and then you see it is very easy that so we are in dimension n. Let us say that n is equal to 2p to simplify. 2p plus 1 case is then you see that on the if you just force all, so U is U1, U2P, you just keep U1, U2, and you force U3 to U2P to be equal to 0. What you get? Then what you get that you are just in the three-dimensional situation. The equations become z dot 1 equals alpha 1, z dot 1 equals u1, z dot 2 equals u2, and w dot all the other remain 0, and w dot equals this key of w, y over 2 u2 minus x over 2 u1. Then in fact you are back, you do not move at all. You do not move at all for the components, the 3 to zp do not move, and here you are reduced to the three-dimensional situation. And since we know that in the three-dimensional situation, the strategy that I described last time, which is the strategy to follow the vector field defined by the distribution on the epsilon tube around gamma is the optimal strategy for the metric complexity, except, but the same, in fact, the case that will correspond to Martinet is the case where KW is equal to 0. So in fact, only the fact that you can smoothly diagonalize shows that you can go back to the three-dimensional situation and shows that in fact this is, you have this equivalence. So co-dimension, co-rank 1 goes to the case of dimension 3 distribution, even including Martinet case. Okay. So now the question, now I come to the question of k equals 2 or 3. And then I need the following, technical level. This is just no more than some linear algebra. But, okay, you have n skew-symmetric matrices that are, I write L1, Ln minus 1, and the last one is n. Okay. You have n skew-symmetric matrices, and you call n of lambda for lambda in n minus 1. N of lambda is just n plus some lambda I Li that I abbreviate by n plus lambda L. Okay, if you agree. I have this. Okay. Now, given a compact body, a compact set B in Rn, I say that this, by definition, I say that this compact set is convex, B is convex in the direction of the vector V, in the direction of V, if you have the following. If there is X star equals lambda V belonging to B, such that, and if there is a linear form omega belonging to, so, Rn star, such that omega X star minus omega of X is positive or 0 for all X in B. Okay, this is convexity, you separate. It is equivalent to the following fact. If you call V the subset of Rn star of vector, if you call V the subset of omega in Rn star, such that omega of this of this V is equal to 1, okay, then there is omega star in Rn star, there is omega star in V, and there is X star equals lambda V in B, such that omega star of X star is equal. There are several ways to write this, but let me choose one. Let me choose the one which is useful. Omega star of x star is equal, of course, it will be the sup of in x in b of omega star of x, and it will be the infimum over omega in v of the sup over x in b of omega of x. And in fact it is equal also, so this guy, okay, this is convexity, just separation by hyperplane. No, some problem?
No.
Okay. So now you have this, and
You draw it to see better what is the cause.
sorry.
Maybe you show the picture. The convex, I mean, what means convex in the direction?
Convex in the direction of V means that you have V, and you have separating hyperplane, and the body B is on the one side of this separating hyperplane. That's it.
Okay. So when you okay,
Yeah.
that's it.
That's it.
In this particular direction.
That's it. Okay. Now, so I need this. In this situation, I need this technical lemma that I want to state very precisely. Okay. I assume that this guy, that the norm of n lambda, okay, in fact, I define like that alpha is the infimum over lambda of the norm of n of lambda. This just the norm of this guy. This I call alpha. And I assume that n lambda. Okay, you can assume more, but to simplify, let me just assume that n lambda has just has simple eigenvalues, whatever lambda. Okay? Let me assume this. Okay. All the eigenvalues of this n lambda are, and I consider the set as a set B. I consider the set B, which is the set of following x prime my. It is, sorry, I put L, okay, no problem. X prime my, x prime L1 y, x prime L p minus p, and n minus 1 y. Okay, I consider B is the set of the values for norm x and norm y smaller or equal to 1. Okay? So in fact B, what is it in my case? It is, as I said, the image of the product of two Riemannian balls in the distribution. It is the image by the bracket modulo distribution mapping, because I remember that these are just the components of the bracket modulo distribution mapping from the distribution to the quotient by distribution. This will be, it will be this the image. The body B in my case is the image of the product of two Riemannian balls in the distribution by bracket mapping. So you get this, and I have this B, and I have the vector V, which is the vector 1, 0, 0. Okay. In that case. And I claim that the theorem is that then B is convex in the direction of V. I prove it. It is quite simple, and there is some very crucial consequence of there are two very crucial consequences of this fact. Now, just to say where I want to go, just to explain where I want to go. If I am in cohort 3, say, this will be the direction of my curve gamma, direction in which I want to move, and there will be two guys here. Then there will be two lambda. Then lambda will be in R2. Lambda will be in R2, and the set of symmetric matrices that have double eigenvalue as codimension 3. Okay? Then again, in my case, generically, if the corank of the distribution is 2 or 3, for this reason, eigenvalues will be simple. Because the bad set in the set of this linear codimension, of this linear combinations has codimension 3, okay? And it is a semi-algebraic set. If you want to have this to have that this as simple, you have to avoid the bad set for all lambda, then you have to project, then this gives you a set of codimension 1 that you will just cross at isolated points generically. So in fact, for coranks k equals 2 and 3, when these matrices will be the matrices of the bracket mapping, and when M will correspond to the direction in which I want to go, then I will be convex in the eigenvalue will be distinct. I will be convex in the direction of gamma, and these consequences of this convexity will hold. On the contrary, this will prove that this shows that if you want to be non-convex on the direction of gamma, then the bracket somewhere you must have a double eigenvalue, okay? It is not possible that this guy, if you are not convex, then this n of lambda must have double eigenvalues for some lambda. So let me prove it, because it is not so hard. Then, since all eigenvalues are different, I can consider, so I can do the following. The largest moduli, the eigenvalues are high alpha. Okay. What I call eigenvalue, of course, is the modulus of the eigenvalues in that case, since they are purely imaginary. Okay. So I take all eigenvalues, write like that, and the largest one writes like that. They can be expanded. So alpha is this infimum. There is no restriction to consider. First, this infimum is reached. Why this infimum is reached? It is reached because these matrices are independent. And why they are independent? They are independent because of the non-integrability assumption. It is equivalent bracket rank condition of the first bracket is equivalent to the fact that these matrices are independent. Then, in fact, this function norm of n lambda is proper function. Tends to infinity when lambda goes to infinity. And then this minimum is reached, of course. And so I write alpha lambda. There is no difficulty to assume that the lambda corresponding to the minimum is equal to 0. It is around 0. It doesn't change anything. And in that case, I just expand. So alpha lambda is equal to alpha plus, so I take the same notation, lambda alpha tilde plus something over the 2 in lambda. And you have the two corresponding eigenvectors that are also smooth. As soon as you have smooth eigenvalue, you have eigenvector is just like that. You have n x equals alpha y, since it is q-symmetric, and n y equals minus alpha x. Okay. What I call the real eigenvector. Then you have this x of lambda, which is equal to x plus lambda x tilde plus the square of lambda, and you have y of lambda, which is equal to y plus lambda y tilde plus the square of lambda again. Okay? And what we have? We have that alpha. Sorry. First we have that. This vector I can take of norm 1, of course. Norm of x lambda equals 1. Norm of x lambda equals 1. And norm of y lambda equals 1. Okay. And if you just write this, that the norm of x lambda is equal to 1, it gives you that 1 is equal to xx plus 2xx tilde times lambda plus second order in lambda, which shows that in fact xx tilde must be equal to 0. First thing. And with the same argument with respect to y tilde must be equal to 0. On the other hand, what you have? On the other hand, you have the following. Alpha or lambda, in fact. So, alpha of lambda, so is equal to the norm of n lambda. Okay? So, sorry, but in fact what you have that also alpha lambda in fact is also equal, you can check for skew-symmetric matrix, if alpha is the largest eigenvalue, you have this, and lambda y lambda, where x and y are the vectors that are defined here. Alpha lambda is just equal to this. And now what I write just the following inequality, that alpha of lambda, which is equal to this, in fact, is larger or equal to the minimum which is alpha, when lambda equal to 0. Okay? I just write this. then I expand on both sides. This gives me alpha plus lambda alpha tilde plus O lambda 2. And on the second side, if you expand, you get the following. You get that it is alpha plus lambda times, there is a term like that, x tilde prime my plus x prime y tilde plus plus x prime L y. Yes, this plus O square lambda. If you just expand, you get that. You get that. You get that. Okay, and this, of course, this guy has to be larger than alpha. What does it imply? It implies that this guy has to be 0. This guy has to be 0 because alpha is minimum. And this guy has to be 0, and in fact these two terms vanish. I show what happens for 1 x prime. No ink anymore. So x prime L y. Sorry, x prime m y. So my, since I am working at lambda equal to 0, my is equal to the n here. So my is minus alpha x tilde prime my. It is x tilde prime alpha x. But sorry, it is this. But of course it is 0 due to this. This due to this fact, this guy is 0. Okay, this guy is 0, and for the same reason, this guy is 0. Okay, and then this implies that x prime Ly is 0, and it is finished because it means that if I consider this vector norm of n lambda star, so okay, if I consider this vector norm n lambda star 0, 0, and the linear form 1, 0, 0 in Rn, it is a linear form that vanishes, that is 1 on the vector, that is 1 on it is a vector that is 1 on the considered, the linear form that is 1 on the considered direction. So in fact this is equal to x prime my, x prime Ly, L1y, x prime Ln minus 1y. Okay? So n, this is equal to the minimum, of course, over lambda. This was my assumption, that this minimum was reached at lambda equal to 0. This is equal to the minimum, and the sup over omega z in the sup over omega z in B of omega plus of omega plus lambda z. Look, it is exactly this. It is just this equality. So, the important conclusion is the following. It is that if you have separated eigenvalues, whatever lambda, if you have separated eigenvalues, you are strictly convex in the direction of gamma, of your gamma dot, in my case, of your given vector, but moreover, in the coordinates where m is diagonal, and the main eigenvalue is the first one, and it means, look, you look at this fact, now you diagonalize m. You can. In the coordinates where m is diagonal, first position you put the largest eigenvalue. What does it mean? It means that all the other matrices, L1 to Ln minus 1, on this block, they are 0. It is what it means, this convexity, if you diagonalize. Because I remind you that this vector, xy, are the couple of eigenvectors corresponding to the maximum eigenvalue. Then, what happens? Then again, due to this convexity, you are back to the situation of dimension 3. Again. Because now, if you consider, again, you can diagonalize everything depending on W, and this diagonalization doesn't change the fact that you are in normal coordinates, etc. Then you can consider that in fact L is alpha 1 minus alpha 1, etc. block, and sorry. And the other matrices, L1, they are the first block which is 0. L2 are the first block which is 0. It is not diagonal, but it are the first block which is 0. Again, so there is one estimate which is clear. There is one estimate for the metric complexity which is clear. It is that the metric complexity is larger or equal to the infimum. So I feel okay, to the sum of dw over alpha 1w times there is a 2 always, as usual, no, sorry, 2 over epsilon square again, but now what is this alpha of w, what is it? This alpha of w, it is the minimum of the norm of n lambda over lambda. It is the minimum of the, it must be the minimum, because you can take such linear combinations, you can take such linear combinations where nw plus lambda w lw. If you take such a linear combination, it means that you are changing the variables in the quotient in the following way. So you do nothing on y, and you put w tilde equals to w plus lambda wy. And this does not change the fact that you are in normal coordinates first, and it doesn't change the fact that the curve gamma corresponds to y equal to 0. Okay, so this is allowed. Then, in fact, the inequality, this inequality we have it for all possible lambda function of w. Then, in particular, we have it for the minimum. In this sense, it works. Then, again, you have the same, this inequality is more or less trivial, and to prove the reverse inequality, what you do now the same that you did in courant 1, now that you are in diagonal form, you consider that all the controls are 0 except the two first ones. Okay? And you are back to a situation in dimension 3 where you get the reverse estimate. Then for courant smaller or equal to 3, we have the same.
So this is actually equality.
So it is equivalence. Actually, it is equivalence, and it is realized in this way by going back again to the three-dimensional case. So as you can see, by the way, the trajectories on the horizontal plane, you have a two-dimensional, always you have a two-dimensional subplane of the horizontal plane in which the optimal trajectories, if you project, they are just circles. Okay? It is like that. So now, unfortunately, this is the best that we could do for metric complexity. For metric complexity, we do not have another result. The reason is that as long as you can go to dimension 2, the tube around the curve is smooth. Okay, and since certainly it is quite clear that the optimal trajectories are on the boundary, when this boundary is smooth in dimension 2, it is a situation that I described yesterday. But in a higher courant, the tube is certainly not smooth. And then, presumably, metric complexity is something very complicated, and we could not calculate it. Then we decided to change and to introduce another concept, which is the interpolation entropy of the problem. It will be a function of epsilon like that. What is the interpolation entropy of the problem? You have your curve gamma. You want to go from gamma 0 to gamma 1 now. Now, you do not want to go by remaining in a tube of radius epsilon. You want a bit stronger. You want to interpolate the curve by pieces that are of length. You want to interpolate the curve by pieces of length smaller or equal to epsilon. Then it is clear that you have it is and again, so among all curves that interpolate by pieces of length then epsilon, you take the minimum, and the minimum of this guy is minimum divided by 1 over epsilon, you call the interpolation entropy. Epsilon. Why interpolation entropy? Interpolation is clear, but why entropy? Entropy because of that. If you take the middle of this piece, and if you take the Sub-Riemannian ball, so this piece has length epsilon, or less or equal to epsilon. If you take the middle, these 2 points are at distance epsilon over 2 of this middle. And it turns out that in all the examples that we considered and that we will consider in all generic situations, if you have on the curve a smooth curve gamma in normal coordinates and you have these 2 points, if these 2 points are in the ball of radius epsilon over 2, then the full segment is inside also. Then in fact, this quantity corresponds exactly to the minimum number of balls of radius epsilon over 2 necessary to cover the curve. And this is called Monroe's entropy, the asymptotics of the number of balls to cover to cover. Then it is reasonable to call this the interpolation entropy. However, this is just generic. There is a counterexample by Jean of a metric cusp in that case, you know. In the ordinary Riemannian situation on the plane, if you have a cusp, this point is at distance epsilon of this point, at distance epsilon of this point, but it does not contain the whole segment in between. Then this situation is called a metric cusp. And there is an example by Frédéric Jean of a smooth curve gamma that has a metric cusp, where this situation does not hold. But it is highly non-generic. Okay. In our case, it will be always true. So it turns out that so this is a new problem. Now I don't want to compute the metric complexity, but I want to compute the interpolation entropy. So before going further, the first question is clearly the relation, in the case that I have already computed, the relation between this interpolation entropy and the metric complexity. And it is quite clear that in all cases that I consider, including singular cases, so where the logarithmic behavior appears, it is quite clear that you have the following formula. The entropy is equal to 2 pi times the metric complexity. Why this? Okay. Everything can be reduced in all the cases that I have treated. Everything can be reduced to the 3-dimensional case. Okay? That's just what I proved. And in this 2-dimensional case, the optimal curve, to get them, you take a cylinder and you consider this vector field intersection with the distribution, okay, like that. What do you do for the entropy? In fact, you will take a tube which is not, which does not contain the curve gamma, but which is tangent to the curve gamma, and that has not radius epsilon, but circumference epsilon. And so it is tangent, and the circumference is epsilon. Here it is around, and the radius is epsilon. And the optimal trajectories will be constructed exactly in the same way in all cases. You construct them just by following the flow of the vector field that you obtain, except in the Martinet case where you have the strategy that I defined yesterday. And then it is clear that there is ratio 2 pi between both. No more than that. So now it is this is the relation. This is true in all cases that I considered up to now. That is the one-step bracket generating cases, or maybe with singularity, up to corank 3. So now there are two possible directions in which to investigate. Either we could, the two directions are the following one. Finish with corank 3, because I finished only in the case of one step with maybe singularity. Or finish with corank 3, or consider higher corank. And in particular, as I told you, there is very interesting first case is the case of a 4 distribution in R10, in which not only there is convexity, there is not convexity, but nowhere the directions in which you want to go are cross the image of the bracket. So let me finish with corank 3. What are the cases remaining? As I said yesterday, there are the cases 2, 3, 4, okay, which is corank 2, and 2, 3, 5. It is the only cases that remain. Because starting from 3, it is okay, if you start with 3 controls, it will immediately give you dimension 6 corank 3. Okay, there is this case also. We treated it, but okay. It is possible to finish with corank 3 now. We have to consider this case. So mostly, this is the car with the trailer, and this is the ball rolling on a plane. Okay. So let me start. Maybe I stop and we continue half an hour after. I see that some people are very tired.